How much power does artificial gravity requiring? Imagine floating in space, feeling weightless, and then suddenly experiencing the pull of gravity again. That's what artificial gravity aims to do. But how much power does it actually need? Let's find out. Artificial gravity in space is created by spinning a spacecraft or a module so that the occupants feel a force pushing them outward, similar to gravity on Earth. The key factors are the size of the spinning structure and how fast it spins. Larger structures can spin slower, which is more comfortable for astronauts. Smaller ones need to spin faster, which can cause discomfort or dizziness. The power needed depends on how much energy it takes to get the system spinning and keep it spinning. To start the rotation, you need a lot of energy because you are overcoming the inertia of the entire structure. The bigger and heavier the structure, the more power it takes to get it moving. For example, a large habitat with a radius of about 50 meters spinning at a rate that simulates Earth's gravity would need a significant initial burst of energy. Once the structure is spinning, maintaining that rotation requires less power. In space, where there's very little friction, only small amounts of power are needed to counteract any losses from bearings or magnetic damping. These losses are minimal but still need some energy to keep the system steady. If the system uses magnetic or electric motors, they are designed to be very efficient, so the ongoing power use is relatively low. Some designs use tethered systems, where a smaller habitat is connected to a central station by a cable. Power is needed to reel out or retract the tether and control the rotation speed. These systems can reduce the mass and power needs compared to a large spinning habitat. In terms of actual numbers, the initial spin-up can requiring thousands of watts or even tens of thousands of watts depending on the size. For example, a habitat with a mass of around 100,000 kilograms might need about 25,000 watts to reach the desired rotation speed. Once spinning, maintaining that rotation might only need a few hundred watts to counteract minor losses. Future space agencies are exploring different ways to create artificial gravity efficiently. Some are considering linear acceleration methods, which use continuous thrust to simulate gravity through acceleration. These systems need steady power over long periods but can be more adaptable for long missions. Overall, the power needed for artificial gravity depends on the size, mass, and design of the system. Large, comfortable habitats requiring more initial power to spin up but less to keep going. Smaller or tethered systems can save energy but might not produce as strong a gravity effect. As technology advances, we can expect more efficient systems that balance power use with astronaut comfort, making long-term space travel more feasible and safe.